Hey everybody. In this section, implicit differentiation, we're going to use the ideas of the chain rule in order to find derivatives of curves that actually can't be represented as functions. So to give you an example, let's just consider this curve. Let's say this is the curve that I'm interested in. Okay. So let's say this curve y this is some I can't represent it as a function of x, but let's say this is some, let's say curve is an equation of x and y. So a bunch of x's and y's, x squared plus x times y minus y times x to the third plus square root of x plus y, and all of this stuff is all jumbled together, and what you get is this big equation. So a bunch of stuff equals a bunch of stuff, maybe something like that. Now this is not a function. Y is not a function of x. Y is not equal to some function of x for any f. Like you couldn't find a function because this doesn't pass a vertical line rule. But the idea, but this is still, suppose, I mean, I drew a little bit of a corner there. But let's actually make that a little bit more smooth so that you believe me when I say that this is a differentiable curve. Differentiable meaning it's a smooth curve. There's no corners. The idea would be, for implicit differentiation, if you were to zoom in on just one portion of it, just on any small portion of this curve, y could be defined as a function of x right there, just for that small portion of it. In fact, you could probably, any point you're interested in, you can find an area around it that y could be a function of x near there. So the idea is we're going to take the derivative and treat y as a function of x kind of implicitly, because we're only going to be, this is going to be true for any small region, and we're not trying to find we never actually intend to write y as a function of x, but what we will be doing is we're going to be keeping our y's in our answer. Okay, so this may not make a lot of sense, but you'll see it when we do some examples. All right, let's take x squared plus y squared equals 25. Now, I'm going to treat y as some function of x. Now, I'm not going to be writing out that y as a function of x, but when I take its derivative, I'm going to treat it like that. So the derivative of y, so like d over dx of y, is going to be some f prime of x, right? And so I should say, let me put it like this. The derivative of y squared using the chain rule is going to be 2y times the derivative of y, right? By the chain rule, which would be like 2y times f prime of x. In fact, it may be easier to just keep it as y prime. So what I'm going to write is actually just, I'm going to call it 2y times y prime. So I'm actually going to have a bunch of y primes in here. And y prime, when I say y prime, that's dy over dx. That's just another way of writing that. In the end, I'm going to solve for that y prime. Okay, let's take the derivative. I'm going to do d over dx to both sides. Okay, well, the right side is the easiest because that's constant, that's 0. Now for the first term, x squared, we'll get a 2x. For the next term, we actually have this already. It's going to be 2y times y prime, because I just solved that over here. So the idea then is I'm going to solve for y prime, get that alone. So 2y times y prime equals negative 2x. So y prime is going to be negative 2x over 2y. That's going to be negative x over y. That's my derivative. That's the derivative of this curve, so to speak. That's my dy over dx for any point on the curve. Now, I need to, so for example, at the point 3, 4, the tangent, I'll give you a sense of what this would look like. So this is a circle, right? And at the point, it has a radius of 5. So at 3, 4, which is maybe right here or so on the curve, if we were try to get an equation for the tangent line, the slope is going to be negative x, which is 3, over y, which is 4, negative 3/4. So the equation y equals 4 minus 3/4 x minus 3 is the tangent line. Also, what you'll notice is if you were to plug in the point, say 5, 0, when x is 5 and y is 0, that's a vertical line, right? That's happening right when the curve comes around, but we can't divide by 0, so the slope is undefined. Well, it's a vertical line, so that makes sense. Okay, here's another curve. I'm going to find the implicit derivative. I'm going to find y prime. And again, I'm going to take the derivative of everything with respect to x. So I'm going to do the d over dx to both sides of this equation, x to the third plus y to the third, treating treating y as some unknown function of x, which locally, like, it behaves like, although it can't be defined as a function of x everywhere. So taking the derivative of the first part, we'll have 3x squared. And we just use the power rule on y, 3y squared. But remember, the chain rule says I'm going to have to get another y prime out of that. I don't know what y prime is, but I'm going to solve for y prime implicitly. Now for 6xy, I'm going to have to use the product rule. It's going to be this derivative over here would be like 6x. Well, I guess I take the 6 out. 6 times x, prime times y plus x times y prime. X prime, this is just equal to 1. So in fact, it's going to be 6 times y plus xy prime. Now I am going to collect all the y prime terms on one side. So 3y squared times y prime. Let's see, I'd have to distribute this 6 to both of these terms. So it'd be 6y and 6xy prime. I'm actually going to subtract that from both sides. I'll keep the 6y on the right, but I'm also going to subtract the 3x squared. I'm going to basically move this part over and move the 6y, move the 6xy prime. Y prime gets factored out of both of these terms. We have 3y squared minus 6x equals, I'll just 6y minus 3x squared, and then finally divide by that expression, giving me 6y minus 3x squared over 3y squared minus 6x. There's the derivative of this curve. At any point xy, you plug those in and you'll get the derivative. Okay, so now this is what this curve actually looks like. And if I wanted to find out what is the equation of the tangent line at the point 3, 3, well, plug that in. Y prime, I'll say evaluated at 3, 3. That's how I'm going to write this thing. Well, that's going to be 6 times 3 minus 3 times 3 squared over 3 times, 3 squared minus 6 times 3. That actually comes out to minus 1. And so the tangent line, say this tangent line here, y equals 3 minus x minus 3. That's the equation for that line. And if I'm interested in finding this point, I can see that right over here there's a point where the tangent line is 0, well, you can solve for that. All right, well, that's going to be 0 only when the numerator is 0. So when is 6y minus 3x squared equal to 0? Well, actually, you can see that that happens at a couple of places. It actually happens down here as well. And you can find that by solving this. 6y equals, actually, I'm going to divide it by 3, so I'll have 2y equals x squared. So there's really two, if I'm going to solve this thing, this relationship allows me to solve it by plugging this in to the original equation. In fact, I'm going to use y equals x squared over 2 and plug that in. X to the third plus x to the, actually it's going to be x to the sixth over 2 to the third, which is actually an 8, okay, equals 6x times x squared over 2. What we get here is, let's see, so I've got 6, actually this comes out to be 3x squared equals x to the sixth over 8 plus x to the third. So I'm gonna, if I, this is to the third on the right hand side. Yeah, so we have 3x to the third, and so I can subtract this x to the third from both sides. So what we get is 2x to the third is going to be x to the sixth over 8. Or in other words, let's multiply through by 8. I'm going to have x to the sixth equals 16x to the third. I'm going to put this all on the same side. Let's write x to the sixth minus 16x to the third equals 0. So factoring out this x to the third, I have x to the third minus 16 equals 0. So when x equals 0, or when x equals the cubed root of 16, we're going to have horizontal tangent lines. And since y equals x squared over 2, y is also going to be 0 for this first point, and for this other, y is going to be, let's see, I have to square it, so this is going to be 16 to the 2/3 over 2. So if I work this out, let's see, let's square that and divide it by 2. That's the cubed root of 32. Oh, no. If I square 16, I get the cubed root of 16. Let's rewrite that as 2 times the cubed root of 2. If I'm going to square it and divide it by 2, that's going to be 4 cubed root of 4 over 2 y is going to be 2 cubed root of 4. That's the coordinate of the second point, which looks right, and it's the y is a little bit bigger than the x is. Okay, check out this other curve. We've got the sine of x plus y equals y squared cosine x. So once again, I'm going to take the derivative of both sides with respect to x. I say that because that later on in later calculus, you'll be taking derivatives with respect to other variables, but we're treating y as a function of x, right? So chain rule says we're going to have the cosine of x plus y. Then we take the derivative of x plus y, which is going to be 1 plus, because the derivative of x is 1. The derivative of y is just going to be y prime. Okay. Now that's equal to, I have to use the product rule here. The derivative of y squared is going to be 2y times y prime times the cosine of x plus y squared times the cosine of x. That's going to be a negative sine of x. So I want to collect, I'm going to distribute on the left to give me cosine of x plus y plus y prime times the cosine of x plus y. And so over here we've got a y prime times the 2y cos x, and then we've got minus y squared sine of x. So we're going to collect the y prime terms on one side of this equation. We'll do it on the on the right. So I'll have y prime times 2y cosine x minus y prime just cosine of x plus y equals, on the other side, we've got, we had the cosine of x plus y, and I'm going to be adding now the y squared sine of x. So I'm just flipping things around. The term, I'm moving this one over and moving that one over. That's why the y squared sine of x, now that's going to be plus instead of minus, and the y prime cosine x is going to be minus instead of plus. I'm going to factor out the y prime. So I've got 2y cosine x minus the cosine of x plus y. And the stuff doesn't change on the other side. This cosine of x plus y squared sine x as the numerator divided by this 2y cos x minus the cosine of x plus y. So again, you can't just plug in an x value and get your derivative. You need to find a point on the curve, and then you'll be able to find the derivative. All right, let's do another example here. We're going to, this is it's what does this look like? I'll show you. So it kind of is, well, this is it's a sort of a circle if you're in a different metric space, but I don't get to, I mean, it's kind of like a rounded square. Let's just call it that. So we're going to find the derivative, and in fact, I want to find y double prime. But let's first take find the y prime. So I'm going to take the derivative d over dx of the left and the right. So I'm going to get 4x to the third plus 4y to the third times y prime equals 0. Derivative of that is 0. So in fact, I'm going to now, I'll put this, I'll solve for this y prime by 4y to the third y prime equals negative 4x to the third. Y prime is thus negative, in fact, I'll so before I do anything else, I'll just divide everything by 4 just to make things a little simpler looking. So if I solve for y prime now, you can see it's going to be negative x to the third over y to the third. I could actually, from here, I could take the derivative to get y double prime, but I think it's going to be easier to do it not from here, but in fact from here, and just to do an implicit differentiation a second time, because I'm going to have to do some power rules and stuff. So let's again do d over dx to give us 3x squared plus, so that's the easy part. Now I'm going to have to do product rule with y to the third times y prime. And that's a y prime. I should be really clear. It's y prime. I'll do my ticks very tick-like. Okay, so hopefully that's really clearly not y to the first power. So I'm going to have 2y to the third y prime plus y to the third y double prime, and of course equals 0 on the other side. If I want to solve for y double prime, what I need to remember is this y prime here, I can actually plug in this expression 3x squared plus 2y to the third negative x to the third over y to the third. That's actually kind of nice because the y to the thirds cancel. And what I've got now is 3x squared minus x to the third. Okay, the derivative of y to the third times y prime, we'll have 3y squared y prime plus y to the third times y double prime, which I don't know what it is. I'm now going to take this expression and plug it in for y prime to get 3x squared plus 3y squared times negative x to the third over y to the third plus y to the third y double prime equals 0. So I've got this y squared and y squared down below cancel, so I'll just have the y. And so let's put this other stuff on the right. I'll have y to the third y double prime equals, it's going to be 3x to the third over y minus 3x squared. And then I can just divide everything by y to the third. Actually, let's do it over here. So y double prime is going to be, so divide each of these terms by y to the third. We'll have 3x to the third over y to the fourth now, minus 3x squared over y to the third. There's my y double prime, my second derivative at any point. And you can see things like, let's see, what does this tell you? Well, I don't want to get too into it, understanding it, but you can get the second derivative at any point on the curve. I'll leave it at that. So here, a bunch of examples using implicit differentiation allows you to find the derivatives of equations that can't be written as functions of x, where y is, it kind of implicitly defines a function of x, but only locally, right? You can't rewrite y equals. In some of these cases, maybe maybe it's so messy, it's impossible or almost impossible to figure out how to write y as a function of x, even though maybe y is a function of x. You could look at the graph and you'd see, okay, technically it is a function of x, but the x's and y's are all so jumbled together that you wouldn't be able to untangle it. So you can use implicit differentiation to find y prime. And the nice thing is, by the chain rule, all of these terms that have, like y prime is just going to be a factor of a bunch of these terms in the end. And you can always just factor out the y prime and then divide and you'll have your y prime. So it's a nice application of the chain rule. All right, well, I'm going to leave it at that. Bye.